Lab 5, ball sliding down the slope. The purpose of the lab was to observe the movement of the ball sliding down the slope with the angle 64 degrees and determine how the energy principle in Newton's second law is applied to the system. The procedure was 1. Observe the ball's movement using the tracker. 2. Construct a B-Python model using the energy principle and Newton's second law. 3. Compare the B-Python model and observe the model's position and motion. 4. Analyze the B-Python model and observe the change in kinetic and gravitational potential energy. 5. Estimate how fast the ball is moving at the end of the slope, which was 2.4 miles per second. 6. Construct a situation where two balls, one at rest in the bottom of the slope and other at the top of the slope, collides. Estimate how this collision affects the ball at the bottom. The ball will speed up and move forward, which is 1.2 miles per second in negative x direction, and ball at the bottom will travel 4.524 divided by the coefficient of the friction of the concrete, which is in negative x, further into the negative x, than initial position. Lab will be focused on the two different fundamental theories, one Newton's second law, 2 energy principle. Newton's second law states changing momentum equals net force times changing time, where the net force is wave force, and energy principle, where the system is mass and earth. It is changing total energy equals changing kinetic energy plus changing gravitational potential energy, where changing total energy equals 0 because no transferred energy to the surrounding or from the surrounding is happening. So in energy principle, K is 1/2 times mass times velocity square, and gravitational potential energy is mass times gravity times height, which is y of the slope. So I'll show you the tracker file. Here I set the coordinate as the ball traveling in negative y and negative x direction, which is in the third quadrant, and the ball's center of the mass was calculated and plugged it into the position x and y graph, and the scale I used was the ball's diameter. So I'll compare this position versus time graph with the B-Python model, which was initial condition was ball's mass was 0.57 kilogram and position and velocity was 0, delta t was 0.033 and gravity is 9.8. I'll show you the file first before explaining other two while loop. So first, this is the position versus time graph, x and y. And second, I constructed the energy graph, which here, shown here. So in while loop, there's two code. First with the Newton's second law, second with the energy principle. So first, I separated the net force into the two components because ball is sliding down in an angle. So the only wave force acts upon the system, and therefore the wave force perpendicular cancels out with the normal force, and only the wave force parallel is acting upon the system. And wave force parallel is wave force times sine theta, which is 64 degrees. And I calculated this and separated into the component and plugged it in here. And for the energy principle, I used the formula kinetic energy and gravitational potential energy. So for this, I'll explain the model B-Python. So yellow arrow was fx, which always points to the left at negative x direction because the ball is moving to the left. As you can see, the force in the y direction, x direction, is much greater than the fy. Red arrow always points down because the ball is moving downwards, and is smaller than the fx because the slope is greater than 45 degrees, which makes the height smaller than the x. So the following is the position versus time graph of the B-Python model, and x increases exponentially as time progresses, and blue y increases slightly slower than x but still exponential growth. So I compared the two position versus time graph, the observed and the model. So the model, represented in red, increased downward more rapidly there because there is only wave force acted upon the system, while the observed model has friction and drag force acted upon it, which makes it slower than the red, the model position. And in here, the y and x, they both have the same comparison. So for the energy, red is the potential energy and the blue is the kinetic energy. Potential energy is negative because the ball is traveling in negative y direction, making h negative, while the kinetic energy, speed is speeding up, ball is speeding up, therefore it's positive. And total energy in green is almost zero because these two energies cancels out. So for the final velocity, I use the energy principle to calculate the final velocity. So changing total energy equals changing kinetic energy plus changing gravitational potential energy. So initial kinetic energy is zero because it is at rest, and final gravitational potential energy is zero because it has reached the bottom of the hill, which h is zero. So v is 2.4 miles per second. So what if imagine ball A initially at rest slides down the slope and gets down to the ball B at rest. At what speed would the ball travel after collision if there is only gravitational force that acts upon the system? 2. How far would the ball B travel from its initial position? So 1. Use the momentum principle. Change in momentum is 0, Pi equals P final. Since this is perfectly inelastic collision, the final momentum is mass 1 plus mass 2 times final velocity. So, use the velocity we found in the energy principle for B1, since that is the velocity of the ball A right before the collision, which comes out to be 1.368. And for V2 is 0 because ball 2 is at rest, and so I get final velocity is 1.2 miles per second for the ball B. So what if 2? Use energy principle to calculate the final distance of the ball B. So changing kinetic trends is magnitude of the net force times magnitude of the change in position times sine theta, where sine theta is 1 because theta is 90 degrees, and kinetic energy final is 0 because velocity is 0 because it comes to stop. And I calculate it and get the final position as negative 4.524 divided by the coefficient of the friction of the concrete which the ball rolls on. Thank you.